But now I would like to present a great speaker as well, Muslim Abu Taha from AWS.
Thank you, Tambi.
Thank you.
Hello, everyone. So until the slides show, oh, they already show, okay, great. But just before I start, could you please raise your hand if you know what Opensearch or Elasticsearch is? Okay, great. So for the people who raised your hands, please keep them up for a second, okay? Who is using it for something that's not related to logs and log analytics? Okay, cool. So we do have some people. That's great. All right, so my name is Muslim Abu Taha, and I'm a solutions architect with AWS focused on Opensearch. I cover EMEA officially. However, unofficially, probably cover the whole worldwide when it comes to Opensearch. And today, what I'm going to talk about is what is a search engine, right? Why we need them, and some of the use cases of the search engines. So we know that we have databases, right? And historically, databases and search engines, they have always been in tandem together, meaning that databases are great as durable storage, right? So you use this database for storing your data. They are great for consistency, right? It means that once you put something in the database, you can ensure that the data is there, right? However, one thing that databases are not great at is scaling for throughput, right? So whenever you have a lot of throughput or a lot of search requests, databases now become some sort of slow on this domain. Now, before the DevOps in the room here start, cutting me into pieces saying that's not true, you can actually scale databases with, read replicas, multi-master strategies, and so on and so on. Yeah, that's true, but I'm talking in a very general sense. And then comes the search engine, right? So again, the search engine, the main purpose of it is to offload the search operations from a database into something else that can scale to accommodate that throughput. And here is a typical use cases that we see search engines being used for, right? So for the people who are using it for log analytics, I'm sorry, guys, I'm not really going to cover the topic in depth today. I will just quickly talk about it, but I will not really go into anything about it. But let's see how things work in the real life and what we see in the market, right? So everything started with text search. So we want to search for text, right? And this is one of the widely use cases that we see. And then some admins or DevOps engineers, they came up with an idea saying, you know what, I have these hundreds of web servers that I need to analyze the logs of, and it's pretty difficult, especially if you're using command line and grep and tools and so on. So search engines are great for search, so why I don't put these logs into the search engine? And this is where we start seeing this analytics and streaming data, right? Where this data is being sent to the search engine, and it's being analyzed in near real time. And then we start to see a new trend in the market, which is the semantic search. So what is semantic search, right? To put in a very simple words, basically semantic means searching for meaning instead of words, right? So I mean something. If I say, for example, my Apple broke. Now here in the room, we are technical, so you definitely will understand that what I mean is my iPhone, my Mac, my iPad, right? The context is understood. And this is what semantic search actually means. So it's the context, how to understand the meaning behind the words. And then we are now seeing a conjunction of Opensearch being used with generative AI applications. So what is Opensearch, right? Opensearch is an open source project created by AWS in 2021, right? It is Apache licensed, so it's a fully open source. It's compatible with Elasticsearch, so it started as a fork of Elasticsearch because at that time, Elastic, they changed the license of the Elasticsearch. So we created the Opensearch as an open source project. It's purely managed by the community. However, AWS still, holds, let's say, a seat in the project. But the project is fully open source, fully maintained by the community, and it's being used by multiple service providers and partners. So we do have a very large community of partners and service providers that are using Opensearch. Now, how you use Opensearch, right? So we have 3 variations of the Opensearch. So you have the open source project, where you can download and put into your environment, right? Let's say your on-prem data center or whatever you want, right? And always there will be somebody who would like to, bring the 12-gear, 30-meter truck, okay, into a place where a bicycle is enough. And by that I mean running Opensearch in Kubernetes, right? So there is always this guy. There's nothing wrong about running Opensearch in Kubernetes. It's purely fine. I love Kubernetes, and I use it all the time. However, you just need to be conscious when you are running it, because it's a resourceful consumer. So you really need to plan it properly when you run it there. And then we have what we call the managed service. So this is the Amazon managed service, right? Where basically we are, as AWS, we are providing you with the infrastructure, with the hardware. We do everything from bottom up to the software. So we will handle the updates, we will handle the security patches, and so on. And then we give you Opensearch, and then you can start using it, right? And of course, this type of service is basically, it gives you some control when it comes to choosing what is the server type and do some cost optimization. And then we got a new version, which is the serverless. And basically what the name implies, serverless means that you don't have to deal with servers. So in the serverless version, you basically just receive like an address, an endpoint, and that's it. You send data to it, and you read data from it. So let's just, try to make the ground flat for everyone, so you're going to start understanding what I'm going to talk about in the coming slides. So let's do a small comparison between a database and Opensearch, right? So in a database, you have the concept of table. In Opensearch, we have a concept of index. Now, you will hear me saying indexes, indices, it's all the plural of the same word. So it's OK. Some people say indexes, some people say indices. I mix, right? Now, we have a table. And then in the table, right, in a database, you have an item, a record, a row. It depends on the engine that you are using, right? Some databases are going to call it row. Some databases are going to call it item, record, depending. In Opensearch, we have a document. Now, a document in Opensearch is a JSON file. Okay, so Opensearch is a single language speaker. It only speaks JSON. It doesn't understand any other language. So whenever you talk to Opensearch, you're going to talk to it using JSON. And in a database, we usually have a primary key, right? Usually it's mandatory in most of the databases, right? And then you're going to have something called the indices or the index, right, of the columns in that table. So you define how many indices or indexes you want in your table. In Opensearch, we only have something called _ID, the ID. So the unique unifier or identifier of your documents in Opensearch is the _ID. And then in your table, you have the attributes or columns or whatever the database is using as a convention for that. And in Opensearch, because it's a JSON document, you have a document field, right? So you have a field and a value, key value, right? And this is how you would translate Opensearch to database for people who are not fully aware of what Opensearch is. Now, in database, we have the concept of insert, right? When you create a record in the database, you usually say, I'm going to insert something, right? And sometimes the statement that you use is actually insert. In Opensearch, we call this operation indexing or ingestion. So if I say ingest a document or index a document, it's just the same, same meaning. And then an index in Opensearch is some sort of an umbrella, okay? It doesn't really have anything by itself. So it's just like a logical name. But what it actually have is something called shards, okay? So an index is just an umbrella for shards. And an index can have one or multiple shards. And these shards are distributed to data nodes. Now, in a cluster, whenever you have a cluster is a set of computers that do a specific task. Usually, a computer in a cluster, we call it node, right? And here, the name data nodes, I think it's, it tells itself, what it does, right? So basically, it's just a node that's going to hold the data, right? But these shards, they have attitude. They behave, okay? So one of the things that these shards do is they like to get cloned. So basically, I'm a shard, and then I can be cloned, right? And the original shard, okay, that existed, we call it primary. The clone, the copy, we call it replica. And again, remember I said that they behave, right? They behave because the original shard and its clone, they don't like each other. They don't like to stay in the same node, okay? So what Opensearch is going to do, because it's a cluster, it usually have a leader, right? So the leader of the cluster is going to say, well, you two are naughty ones, so I'm going to put you apart from each other. So the primary should exist in one place, and the replica should exist in another place. And this is how Opensearch is a distributed system, and it ensures durability and availability of the data, right? Because you have primary shard, and then you have replicas. And the replicas, they are a dynamically configured option, meaning that you can have one or more replicas, right? So you are not limited to only one. And again, these shards, they are troublesome, meaning that they consume resources. So all of the resources of the node, the CPU, the memory, the network, basically they will be spent in these little beautiful shards. All right, so what are the main top factors that you need to consider when you have a search workload, right? So for the log analytics, usually it's easy, right? You just need storage, put your logs there, and start doing this very beautiful graphs. Search is a bit different. So the most important thing is relevance, right? This is a search engine. It's not an exact match engine. So you are not like going to a database saying that, give me every record you have that has ID 1, right? This is something that it should give you documents that are relevant to your intent, that are close to what you mean, okay? So relevance is the first thing. It's the most important one. And then, of course, we have the search user experience. So imagine now that you have this beautiful website, and you're allowing people to search, but you're telling them, well, you can search for dates, but only in ISO format. So it needs to be year, month, date. So it's pretty complex, right? It's not a nice user experience. Search engines, they make things pretty easy for everyone. And then there's performance. I will not focus too much on performance, because this is a whole topic by itself. We usually spend like hours talking about it. Anyway, so let's have a look at how the search itself, evolved through time, and let's see how we got from from lexical to semantic. So what is lexical? Lexical basically is a term match, a keyword match, a word match, right? So here we have the Amazon.com website, right? And basically, here I'm searching for, I'm not sure if it's clear, but I'm searching for an olive couch. Okay? And you can see that the items on top are the closest to what I mean. So by the way, it's a olive foldable couch, right? So you can see that the first few are foldable, some of them are olive, and in the bottom, okay, they are couch, but they are not fitting the whole requirement. And also, the search allows you to do what we call the faceting or grouping. So you can just think of facet just like a group by in a database where you're grouping, by certain topics. So it makes things, easier to search and to filter. So lexical, again, it's a keyword match. It's an exact match for the word. So if I say couch, it needs to go through all the documents and find the documents that contain the word couch. If a document doesn't contain that word, it will not be retrieved. So let's have an example that I created only for this session. Okay, I don't know if it's clear, but I'm going to read. So these are two documents that I created just as a sample, right? And basically, the first one, it says XYZ Hotel has all facilities, blah, blah, blah. And then we have the word family. So just keep family in your mind, okay? Second one is saying that set in Cape Town. By the way, Cape Town is a city in South Africa. I lived in Cape Town, by the way, 2 years. So if you guys have any vacation plan, put Cape Town in your list. You will really enjoy it. Anyway, so here, set in Cape Town, blah, blah, blah. In the end, what I'm saying is very convenient for parents with children. So parents with children is the other side of family, right? Usually a family consists of parents with children. It could mean other things as well, right? A team in a company could be a family as well, but here let's focus on this one. So I just highlighted this. And now I'm going to do, what I'm doing here is the ingestion part. So basically this, in Opensearch, we have something called the dashboard. It's just a UI for the Opensearch in which you can interact with the service. And then it has a console, a developer console. So basically, you're going to talk to it through this console or directly through a CLI if you want to. So you're not really limited to the console. And here what I'm doing is I'm creating a document, 2 documents, the documents that I showed you before, right? Now, on this screen, I have a search. Remember when I said that Opensearch understands only one language, JSON, right? So JSON is for everything. You'll see that I'm searching using JSON, I'm retrieving documents using JSON, everything is JSON, okay? Now, I have here a query. I don't want to focus on the syntax, okay, because this is not really the topic, but just FYI, this syntax is what we call DSL, domain-specific language, okay? But again, we're not really focused here. And here what I'm saying is match all. I'm not really setting any word. Just give me everything that you have in your index. And we can see here that we got 2 results. So the first one, right? This is set in Cape Town, blah, blah, and the second one. And on the top, okay, there are some information that could be useful. Maybe the first one is the most useful information for any developer, which is the took. Took, basically, it means how long it took the engine to process and to retrieve these documents. Okay, so if you are into performance and you are into SLAs and you need to ensure that every request needs to respond in a certain amount of time, the took is your friend, right? Keep an eye on it. Now here we see that we have 2 documents. Nothing really fancy, it's just a normal retrieval. It's just like I'm doing a select star from my table. It's on the other way. Now here is where the magic's gonna start happening, all right? So I'm doing a query. I'm searching for the word family. And how many documents I got, the hits value is 1. So basically only 1 document got retrieved, which is the document that contains the word family, right? But remember my second example, what it was? It was parents with children, which should match, right? Because it is relevant to what I'm looking for. It's an hotel, it has rooms for parents with children. But Opensearch is dumb. So it only understood this single, you like the word, huh?
We have the same problem in our too.
Cool. So, all right, so Opensearch is using, it's lexical, it's doing a keyword match. Family exists in document? Show it. Doesn't exist? Sorry, I'm going to show you. So this is another representation of the issue, right? Here I'm just searching for this, Xbox. Does this game works with my Xbox, right? And then something is going to happen inside the engine, the Opensearch engine, right? Which is the first thing is the inverted index, okay? What is an inverted index? To put it in a very simple way, if you have any encyclopedia, right, or any book, if you go to the end of it, you will find the index of words, right? And you'll find, for example, Jordan. If you want to Jordan, go to page 5, 10, 100, so on, right? So this is an inverted index. It's just, it reads the document that you have, take the words, and then start matching, saying, okay, family showed in document 1, document 2. Cape Town showed in that document, and so on and so on. And then we have the TF IDF. IDF is not the infamous IDF, okay? It's something else, so don't worry about that. TF is the term frequency, so how much a term showed in the document, okay? And then the IDF is the inverted document frequency, okay? Again, it's purely math. I don't really want to go into this topic. But here it's not clear, but anyway, here is the broken of the document, into words, and then here are the words and mapped with the document number that it shows on. And then we have this, this black magic here that does the scoring. Remember when I said relevancy is important, right? So how Opensearch knows that a document is relevant to what you are looking for? Basically, it's through this scoring math, okay? So it's going to do this math based on the frequency of the word, how rare that word is in document, and so on. So again, it's black magic. We don't really want to go into that. However, if you look at the result is very, I will say, inaccurate for us, right? Because what Opensearch looked for, every single word in my query, okay? The first one is correct, right? It matches what I want. I want something for my Xbox, although I'm a PS user anyway, but okay. So the second one is not really, or let's say the other results are not really relevant to what I'm looking for. So another thing that's happening in the search world is the personalization of the results, okay? I'm pretty sure you guys have used systems online, purchased things online, and most probably you hit Opensearch or Elasticsearch in a way or another, right? If you purchase something in any platform, you will usually see something called users who bought this also buy, right? So this is some sort of personalization, meaning that because you purchased Xbox, maybe you like, PC games. They are related in a way or another. So this is some sort of personalization, right? And they got better and better with time as you gather more data. And then, okay, something happened, which is semantic search. Remember my hotel, I have the word Cape Town in it, right? Cape Town is where? In Africa, right? And I'm planning to go on vacation with my family, and I want to go to Africa. So show me, a stay. I want to stay in Africa. Now here, there is something called neural. I will talk about it in a bit, okay? Just keep this in mind as of now. And then here we have a model ID. So model here is for the machine learning model. Okay, I'm going to come to it, but just keep these two in mind, right? And then when I search, okay, just to remind you, these are my two documents. The first one doesn't have a place at all, right? It only have the word family. The second one is set in Cape Town and doesn't have the family, but it have the parents and children. And when I do the search, what's the first document I got? Set in Cape Town, which is in Africa, right? But I also got the second one. Any guess why I got the second document? Even though it's not related, it doesn't have Africa, it doesn't have anything. But any guess why it actually showed? Sorry? Okay, stay. Well, usually that's the thing, right? So an hotel is a place. It needs to be in a physical place. And because it don't define where the hotel actually exists, it could be in Africa. There is nothing that says that it's not in Africa, right? So the engine here thought, okay, it might be relevant. And then we have the score. Remember when I said the relevancy? Here I have a score, and here I have a score, and I see that the one on the top has a higher score. That means that's more relevant to the query than the other one. So just being conscious of time, moving on. And here's the same thing. When I search for family, okay, using the semantic search, I got the one that actually has the word family in the top because it's like semantic and keyword match at the same time. So of course it's higher than the other one. So black magic here again. Let's have a look at how this works. So does this work with my Xbox? Okay. In the previous example, we saw that the text is going to go to the inverted index, and then you have the IDF, not the infamous one, okay, doing it so on. Here we have something completely different. We have something called vectors, and by now I'm pretty sure that you got sick of hearing vectors and AI, but I'm going to keep this very simple. So inside Opensearch, what's going to happen is that we create like a virtual world, okay? A virtual space where we put these vectors, okay, close to each other, okay, based on the context. And this is why, for example, the word hotel, okay, it's in the context of a place, it's in the context of a physical location, it's in the context of a city maybe. So there are so many things that are there, right? And then we, again, do black magic using a similarity algorithm, to find out the vectors that are close to each other. So because word hotel is in this side, it's closer, to place, for example, rather than closer to, let's say, to the animal world, for example. So again, I don't really want to go through the math. It's just about the representation of it. So another thing that we see emerging a lot is the multimodal image search. Up to very recently, we only search through words, right? You go, you type what you want. Now I see, well, Tambi is wearing this very nice shirt. I took a picture of it, and now I can search through the picture, right, instead of the text. Or it's just like, I'm embarrassed to ask him, from where he bought it, for example. So image search could help with that. And also, we now see the generative search, or let's say the search that is being used with generative AI, where you are powering your search by generative AI. And this is usually RAG. I have a slide about RAG, to keep it pretty simple. So moving on. So just to recap, how the search has been evolving throughout the years. We started with the keyword search, and then we improved that with personalization, and now we have the semantic, okay? And now we have the conversational search. So let's have a look, at the types of semantic search that are supported in Opensearch, okay? So we have 4 types. We have the semantic search, we have the hybrid, the multimodal, and the neural sparse. So let's take them one by one. Again, remember when I said vectors are, a representation. We have this virtual world, and then we put these vectors close to a specific context, right? So this is a representation of it. However, in computer, okay, a vector is only numbers, right? You have a text, and then these vectors, or this text is converted into numbers. So how do we make this look like that? So basically, we do it through a machine learning model, right? So we bring these little black boxes, okay, put them in between, okay, and then we send the text to it. So what I did in my previous example is that I took the description, the hotel description, I passed it to a machine learning model, and I got these numbers, right? All right, so just 2 things here about vectors, just to make it pretty easy. In math, a vector it's a line, right? It's a line that has an orientation and has a specific length. In AI or computing, when I say a vector, or the vector dimension is how many numbers in the array. So vectors, again, they are array of numbers, okay? And well, I don't want to say that the bigger the array is, the better the relevance. It's not always the case, but for now, let's just take it that way, right? So some machine learnings are going to create vectors for you that are 300 items. GPT model 2, for example, equates, if I'm not mistaken, 1,600. Okay, GPT-4, I think, close to 13,000, something like that. Anyway, so in theory, the more numbers you have here, the more context you have inside, your vector. So imagine now if we have this ability to convert all of our data to vectors. Imagine the possibilities that you can get, right? And by the way, for people who know applications like Shazam, for example, although they are not using vectors, but the concept is similar in a way or another. So they convert the music into a representational form, okay, math or whatever, and then they can do the search on top of it. Amazon Music, by the way, is using actually vectors and embeddings and so on. So this is a counter example that actually is using vectors. Okay, another black box or another magic here. It looks complex, but it's pretty simple. Okay, so let's look at this side here. Remember when I was saying about enterprise data, right? We have this enterprise data, and we want to use them to convert them to vectors, so we can then start doing this similarity search, semantic search around it, right? So here is I'm passing my vectors to a machine learning model. And again, what is the ML? It's not my topic. I'm not in the data science field. It's really up to you guys to decide what is the right one. But again, what the model is going to do is going to give you these vectors. Okay, forgot now about sparse and dense. Okay, and then we're going to put them inside Opensearch. So Opensearch now started to act as a vector store, right? Not only a document store, but also a vector store. And then we have our cool developers that are building these nice tools, using this. Now, here you can see that you have this model, okay? We usually say the models, they are like black box. It's some sort of kindly true or partially true, meaning that we know what's the math that is inside the model, but what we don't know is the input and the output, right? Because you don't know what will be the output if you give it a specific input. So this is why we call it black box, but it's not really that black box. So in Opensearch, you have multiple ways to achieve this integration, right? So you can have your ML sitting wherever you want, okay? You just send your data to it, got the embeddings, put it in Opensearch. You don't really care how you do that. If you really want to spend a lot of money, you can take the model and put inside Opensearch. And instead of focusing on searching, you're going to start now focusing on machine learning and training your models. So you're going to pay a lot for that. So I don't recommend it. But you can actually put your model inside Opensearch directly. Okay? And then we said, you know what? Putting the model inside Opensearch is kind of expensive. So let's help our users do things, achieve what they want, simplicity, but in a cheaper way, which is through what we call the AI or ML connectors. So a connector is a plugin in Opensearch that you can say, I'm going to use a third-party machine learning platform. Okay, and the platforms we support, one of them is Amazon Bedrock. So Amazon Bedrock is just a way to interact with large language models through an API. It makes things easy. But that's not the only limitation. You can use OpenAI, you can use Cohere, you can use SageMaker, or you can use even your own platform. So my colleague Hussein was talking about his platform. That would be one good candidate to use with, to use as a connector. So what happens now is that you don't have to deal directly with the ML model. You just send everything to Opensearch. And Opensearch is going to communicate with the ML platform, get the embeddings for you, and store it into Opensearch. So here is a representation. Remember when in my example I say that keep the model ID in mind, right? So basically here is a connector that I have to Bedrock. And here I'm just sending a text. Hello, right? And what Bedrock is sending me the vectors, the embeddings. Now I didn't print everything because this is a 1,500 vector, so it will be very, very large to show in the screen, but here is the idea. The text that I showed before, the example of the hotels, I hide this part just for the example, but this is how actually the document looks like. So I have the first part, which is the description, the human readable text, and then we have the embedding part. And when I was doing the search, say in Africa, I was actually doing a similarity search, KNN. Who heard about KNN? K nearest neighbor, yeah. So I was doing a K nearest neighbor search on this part. So we saw the semantic search, right? Now we have something also called hybrid search. And hybrid search is a way to combine two things together. So basically it's a way to combine the lexical keyword matching and the KNN feature or the semantic feature, right? So why do we need a specific function for hybrid? Well, mainly because the scoring system is different. So in semantic, we always have numbers that are ranging between 0 and 1, right? In the TF, IDF, infamous IDF, okay, function, it creates numbers that are actually bigger than 1. So you have an inconsistency in terms of scoring system. So the hybrid here, it does this normalization, ensuring that you have a consistent system. So here's an example of it. So basically here is, so the first one, we have a normal match, matching for family. And the second one is the neural, remember? So the neural is actually the ML plugin of Opensearch where it's talking to Bedrock to get the embeddings and so on. So the neural is the plugin that does the magic. So moving on, we have the multimodal. And again, the multimodal is where you can actually mix pictures, audio, any representation of files, okay, with the text. So you can search, for example, I want a trouser, and here's the picture of it. So you can mix, so basically the picture could look into a specific thing, and the text could look into, for example, in the brands, for example. And then we have, which one is this? Then we have the sparse, okay, the sparse neural. So we are converting text to vectors, right? Now vectors are dense that there are so many, because you saw, for example, here we have like 1,500, but we can go up to 16,000 sometimes. So they are super dense, and they consume a lot of memory, by the way. And this is probably I forgot to say. So if you want to use semantic, and you have very, very large vectors, you're going to need quite a big amount of memories. Start thinking in terabytes, okay? So somebody laughed. Okay. Now we have a better approach, which is using the sparse vector. And basically, the sparse is a different way of calculating the weights, okay? I'm not going to talk too much about it, but here we are not really converting into vectors, but we are converting to words that are close to certain words. So it's a different way. So you can think of it in a way or another like synonyms, right? PC, laptop, they mean same thing in a different way. And then we have this little guy here, the RAG, okay? Not rat, RAG, which is the retrieval-augmented generation. So what is RAG? So Tambi, I'm sorry, I'm going to pick up on you again, okay? So Tambi created this very amazing software, okay? And I am an LLM. I'm a very good writer, technical writer. And Tambi came to me and said, Muslim, write a documentation for my application. I was like, say no more. Here it is. And Tambi looked at the document. He was like, what? What is this? What a toot, toot. A lot of toots, because he didn't really like what I showed him. And he was like, Muslim, you are hallucinating this? This is what hallucination actually means, right? Is when the LLM gives you something that it doesn't really know anything about. And this is what I did. I actually hallucinated because I don't know what his software actually do. And then Tambi was upset, and he said, you know what? Go learn. And now I start the fine-tuning journey where I start reading about his application, seeing what it does, and so on and so on. And then now Tambi is still angry with me because he's paying a lot. He's paying me by the hour, right? So he's like, Muslim, I'm wasting a lot of money with this. You know what? I'm going to give you the project objectives, okay, the requirements, and what we did to implement it, and now write based on this. So what Tambi did is that he gave me some files to help me writing. So this is what actually RAG is, okay? And this is what Dr. Hassan was talking about before, right? So it's just helping the LLM by providing it context that is close to what you are looking for. So if you want to see how you would use RAG and how Opensearch can be part of that, basically here is where you have a document. Let's say you have a PDF, and then you chunk your PDF into pages and into paragraphs, right? And then again, you convert these paragraphs into embeddings, vectors, right? And then you store them in a vector database. And again, here, vector database could be, Opensearch is a candidate. It's not the only candidate in the market, but we recommend it because you get the extra features of search with it, right? So that's basically how it would work, right? So now I want to search. So when I want to search, I have my question, right? I'm going to convert the question into embeddings, and then I'm going to do a KNN search in Opensearch, get the relevant documents, and then I'm going to feed it back again to the LLM with the question, and then the LLM is going to be able to generate a more consistent answer that's closer to what I want rather than the hallucination part, right? And basically, this is the same thing that's applied when we, sorry, this is the last one. So basically, this is the same thing that's applied when you have the chatbots, right? So the chatbots, when we say ChatGPT, The actual LLM is GPT. Chat is just an application that's using the GPT model, right? But under the hood, basically, it is working in a similar way. Maybe not exactly like that, but it's very similar to this structure. It gets the texts that are relevant to what you want, and then it shows you the answer. And with this, you can actually build chatbots that are able to answer questions in your documents. And I've done I've helped some customers doing this, where they're actually feeding the PDF file into Opensearch, and then they can actually start chatting with the document. Show me the page, or show me blah, 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 that something happened. And with that, I conclude. So, well, I got 23 seconds, so I'll not be able to take questions on the stage, but if you have anything, you can find me outside. And with that, thank you very much for attending. Thank you.
Thank you, Muslim.